So, hi everybody, I'm John Larrea from the University of Edinburgh, and in this session I'm going to introduce you Nervion. This work has been done in collaboration with my advisor Mahesh from the University of Edinburgh and Kobus from the University of Utah. So with the introduction of release 15, the 3GPP has defined for the first time the 5th generation of mobile networks, or 5G. 5G has brought a lot of new changes to the core network architecture, such as the softwareization of the components, the usage of a new cloud-based architecture, the fragmentation of the existing components into microservices, or the complete separation between control and data planes. All these changes have brought a lot of attention, not only from the standardization bodies like 3GPP, but also from the research community and open source community. As a result, we've seen in the last 4 years, many core network proposals that tries to deal with existing problems of the EPC, which is the core network in 4G in the first generation. Some examples are, for instance, Mobile Insight, which is a research project that tries to deal with the scalability limitations of the 4G core network. Similarly, from the research community, we got ECHO, which tries to deal with the availability and resilience requirements of the core network. On the other hand, we got open source projects such as OpenAir Interface or Open5GS that tries to provide a standard 3GPP implementation of the core. However, the question that we got is, among all these different options, which one should I use for my particular use case, right? So in order to determine that, we have to compare all these core networks. And to do so, we have to follow just this simple 3-step algorithm. First of all, we have to select a common scenario for all of them, suppose IoT. Then using that scenario, we have to stress the core network. And finally, we have to get the metrics and compare between the metrics, right? The problem is that each of these different core network implementations have been evaluated with a different tool. Therefore, you cannot go to the papers and compare directly between them. So the only option left is to reevaluate them all using a single tool. So if we take a look to the tools that have been used in the literature to evaluate core networks, we can differentiate 4 main types of tools or methods. First one is using real devices. This is the most intuitive way to test a core network. You just get some devices, get some base stations, and you connect them to your core. However, as you can imagine, this approach is super expensive, and it is really hard to maintain large-scale platforms with commercial hardware. Alternatively, we got simulation models. Simulation model basically is they replace the interface between the RAN and the core by a mathematical model that mimics the behavior of that interface. However, the problem with this approach, as I said, they replace the interface. So you cannot use a simulator to test a commercial core network. The third option is trace-driven evaluation. Trace-driven evaluation are quite simple. You just get a trace and you replay the trace. The problem with this, actually, we have 2 problems. One of them is how you get a trace. In general, those traces are provided by operators. As you may know, operators in general do not share much data. And even if you are lucky and you get a trace, you have the problem of generalize. It is not possible to generalize from one trace that has been captured in a mobile broadband scenario to generate IoT traffic, right? So we cannot use this method to generate any kind of traffic. And the last option, which is the most common in the literature, is RAN emulation. A RAN emulation basically, or a RAN emulator, is a software or hardware tool that replaces the RAN and replicates the behavior of the RAN. However, if we take a look to the tools that have been used in the literature, I mean the RAN emulators, we can see that there are several limitations in all of them. We got limitation in terms of scale. Most of them only allows you to emulate 1 UE, at most 2 UEs, and 1 base station. We got limitation in terms of what kind of traffic we can generate with these tools, both control and data plane, the amount of scenarios that we can emulate. Also, we identified that a significant number of these tools were not even standard compliant, so we cannot use them to test standard compliant core networks or commercial core networks. And finally, we identified that all of these are either for 4G or 5G. So you can not test a 4G and a 5G core network with any of these tools. So we decided to convert this list of limitations into a list of 4 goals that we would like to have in the ideal emulator. These goals are scalability, flexibility that refers to the load generation, automation and programmability, and finally the tool should be 4G and 5G standard compliant. So to this end, we present Nervion. Nervion is a cloud-native RAN emulator that implements all these goals as features. And we did that by using different techniques. For instance, for the scalability aspect, we decided to abstract the RAN internals. We refactored the RAN. We also use containers to containerize each of the elements of the RAN. And finally, we orchestrate all with Kubernetes. For flexibility, automation, and programmability, and therefore reproducibility, we use something called Nervion scenario that I will describe later. And finally, we were able to provide a solution which is 4G and 5G standard compliant by decoupling the interface between the run and the core. So if we take a look to the design of Nervion and we compare it with the standard architecture that is used by all these tools, we can see clear differences. In the standard architecture, we got two elements in the run, the UEs and the base stations, and both of them implement control and data plane. So if we think from the software perspective, because at the end, this tool is going to be a software tool, we can have a situation in which we have 1,000 UEs, all of them connected to the core network through a single base station. And in that particular scenario, all the control planes in the UEs goes to the core network through the single core, control plane in the base station, creating a potential bottleneck. The same thing would happen for the data plane. So potentially in the base station, we have two bottlenecks. So in order to overcome this problem, we decided, first of all, to decouple the interface between the run and the core as a separate module. We did that because the only thing that the core network is able to see is that interface. So everything behind that interface is completely transparent for the core network, and therefore is meaningless for it. So we separate this interface and we refactor all the internals of the run. We move the control plane of the run to the base station, and we move the entire data plane to the UEs. In that way, both control plane and data plane in the run have direct access to the core network without having to go through an intermediate hop to reach the core, like in the standard architecture. We implemented this in Python and C, although most of the code is C. And we integrated it with Kubernetes. The reason for this is double. First of all, because we use Docker to containerize the elements of the run, and Docker works great with Kubernetes. And the second reason is because Kubernetes gives us scalability, since it allows us to deploy Nervion in a large cluster. And finally, we provide a 4G and a 5G implementation. The way Nervion works is quite simple. We got the Nervion controller, which is an orchestrator of the run, that receives a file from the user. That file is called Nervion scenario. That file contains all the details about the emulation. Then the Nervion controller interacts with the Kubernetes master node through the Kubernetes API to create as many pods as needed to perform that evaluation. And then once all the pods have been created, the Nervion controller just orchestrates them. So before going into the details about the evaluation of Nervion, I would like to spend one slide talking about the Nervion scenario. The Nervion scenario is just a JSON file that contains all the details about the emulation. And therefore, it provides us programmability, because within a single file, you are able to define the entire experiment. It also provides you automation, because once you submit this file to Nervion, you don't have to supervise the experiment like with other tools. It provides us repeatability, because within a single file, you can repeat the experiment anytime. And finally, it provides you flexibility in terms of the load that you can generate for both control and data plane, thanks to the usage of two particular parameters in the UE that allows us to define which behavior do we want to have for a particular UE for both control and data plane. So now let's switch to the evaluation, which is, I would say, the most important part of Nervion, because this tool is meant to be used by the community and therefore has to be tested correctly. And the first thing we evaluated was the correctness of Nervion. What is correctness? So a run emulator is correct if the effect that it produces within the core network are the same as the effects that you can produce with a commercial phone. So based on that definition, we decided to monitor different core network implementations while we were generating different kind of control plane action and generating different kind of traffic loads with different runs. In particular, we use, of course, Nervion. We use some open source emulators. We use a commercial emulator, OpenEPC, and also we use a physical phone, a commercial phone. And we proved that there is no difference between the effects that Nervion produces within the core and the effects that a commercial phone produces within the core, therefore proving that Nervion is correct. We also evaluate the efficiency or the performance of Nervion. To do so, we compare Nervion against two types of emulators. First of all, we compare Nervion against those emulators that implements the entire radio stack, like Open Air Interface or SRS. And we also evaluate Nervion against other type of emulator that only implements what is essential for the core network, like Nervion. which are represented by UA SIM and OpenEPC. And we prove in the paper that the performance of Nervion is much better than any of these alternatives. In terms of scalability, we evaluate two versions of Nervion. The standard version or the full mode version of Nervion that contains control and data plane. We were able to get up to 110 UEs per Kubernetes node. Later, we discovered that that limitation was imposed by Kubernetes itself and not the design of Nervion. So in order to overcome that limitation, we decided to implement what we call control plane only mode. That, as the name suggests, disables the data plane in order to get more scale for the control plane. So we did that by removing the UE from a pod, and we now replace it by an application, a multi-thread application actually, in which each thread is a UE. With this mode, we were able to get up to 10,000 UEs per pod. That translates to around 1 million UEs per Kubernetes cluster. Sorry, Kubernetes node. We also show in the paper several use cases that can be generated using Nervion. For instance, you can perform scalability comparisons. In this particular example, we are evaluating 6 different core networks, showing that the most scalable solution is a mobile stream. We also show how we can perform latency comparisons by stressing the different core networks with a fixed load and then measuring the latency within each of the different cores to see which one performs better under stressing situations. And finally, we also show how Nervion can be used to generate different kind of network patterns. For instance, here we are showing how Nervion can be used to generate IoT behaviors or mobile broadband behaviors. And as you can see, those two graphs, the red line represents the control plane traffic, whereas the blue line represents the data plane traffic. And both of them, both sides, are completely different, showing that with Nervion Virtual, you can get any type of UE emulated. Before finishing this talk, I would like to say that Nervion can be used right now in the Powder platform. It's free to use. We have created an open source profile for the Powder platform that allows you to create a Kubernetes cluster. It also allows you to customize your Kubernetes cluster by specifying the number of Kubernetes nodes that you want in your cluster and the size of each node. And then on top of that, it instantiates Nervion. This profile comes with 6 different core network implementations that are ready to use with Nervion. However, if you want to test your core network, it is possible to instantiate an empty machine and you can deploy it there, or you can modify the profile to include your special setup for your core network. And finally, I would like to say that not only this profile is open source, but also Nervion is open source. So if you want to extend it to support more control plane events or more data plane traffic generation, you can do it because it's open source. So if you are interested about the details of Nervion, I suggest you to access the full paper. Or if you want to use Nervion, we have released a complete guide about how to use Nervion on this Powder profile. Thank you.